Well, there was 3 people in the class, but usually I was only one.
Yeah.
What?
Yeah. All right. And let's see. The reason this class should be recording this, what I am, is because one person went to the dean and said, "I need to have this class," and then so I was basically indirectly told, run a special topics class for that person. I said, no, I'm not going to do it for one person. If anyone else wants to do it, they can be in it too. Now, that one person. So, but okay, never mind. All right, so where we left off last time, I think we were starting 2.3 at the beginning of 2.3. You said that before, I remember now. Matrices and inverses. Let's pause for a moment and say, what do we mean by inverse?
Well, it would be whatever you, multiply by the original matrix and get a identity matrix.
Okay, that's exactly what we mean in inverse of a matrix. That's exactly it. But inverses in general, we have multiplicative inverses, we have additive inverses, we have lots of things we call inverses.
Derivative and the
integral, yeah, those are basically inverse operations of each other. So you have inverse, I'll call it mathematical operation, like subtraction is the inverse of addition and multiplication the inverse of division and vice versa. Then we have function and inverses. One function undoes if y is equal f of x, then x equal g of y. Those are inverse functions of each other. And then you have, as you pointed out, operations that are inverses. Integration undoes differentiation and vice versa from that too, within a constant, going one way. Okay. So what about matrices and their inverses? Well, it's kind of like a little bit of both of those. And actually it gets almost back to, almost, not there, to the multiplicative type inverse. For instance, if you're solving an equation, oh, I'm sorry, I forgot that. Okay, saving the bub and still saving the bub. Okay. If you have an equation, ax is equal to b. These are numbers, not matrices, not vectors. These are this thing. How do we go about solving that? Ax equal b?
These are numbers?
Yeah. This is an equation, algebraic equation. Yeah, divide both sides by a. And dividing by a is the same thing as multiplying by 1 over a, right? Which is the multiplicative inverse of a. So you could call that a to the minus 1 times a times x is equal to b times a to the minus 1, or minus a to the minus 1 times b. That probably would have been the better way to write it. And this gives you x is equal to, I'm going to write it this way, a to the minus 1 times b. Otherwise, you might think the BA is both the inverse, okay? Now, that was back in the algebraic sense of an inverse, okay? We're going to do something very similar to that with matrices, okay? 1 over a is the multiplicative inverse of a, because a to the minus 1 times a is equal to 1, right? 1 over a times a what? Okay. Well, in matrices, we're going to do the same thing, except we don't really have, what is our multiplicative identity in matrices? And you said it before, I've just said the word, the identity matrix. 1 on the diagonal, 0s everywhere else. They have to be square. And sure enough, if erase, nope, it's not what I wanted, this one. Okay, if we had, okay, here's a definition. an n by n matrix, by the way, okay, I hate that, n by n matrix, A, what we're going to call that, I want to call it A sub n, because it's square, okay? Okay, an n by n matrix A is invertible, okay? And another word for that is non-singular. Okay? It's invertible or non-singular. Second?
Non-singular meaning.
Okay. Why they use the term, I'm not really sure. But it means, okay, get this a square matrix, right? If you do your row reduction, okay, and you do it all the way, if you come up with the identity matrix, then it's invertible, and it's called a non-singular matrix. If you wind up with things here and a row of zeros at the bottom, that would be a singular matrix. Okay. Why they call it singular, I don't know, but that's not invertible or a singular matrix. Now, it's a weird choice of words in my mind for mathematicians, because in complex space, in complex number system, a singularity is a place that's is not definable. You know, I think of the universe, a black hole is a singularity. Things don't really work around that like they do everywhere else, you know. And so I don't know why they call a matrix singular and then non-singular. It seems like it's almost backwards in that kind of concept. But those are the two words. Invertible means non-singular. Non-invertible means singular. Okay. Maybe we'll run across something that'll make sense, but I don't recall where that's going to be. I can't recall that they address that anywhere. Now, if A is an invertible matrix, then there's some other matrix B such that A times B is the same as B times A, and these are both your identity matrix of size n, I sub n.
They're basically inverses of each other.
Yeah, they're inverses of each other, just like.
And they're commutative.
And what?
And they're commutative if they're the inverse.
They're what? I can't hear.
Commutative if they're the inverse.
Yeah, and that's why I always said most matrices aren't commutative. But when you do run into them, they're special ones, and this is one. These that are invertible matrix does have an inverse, and if you multiply, just because it's an invertible matrix, you can't multiply it by any B and make it be, you know, it's only its inverse that it commutes, but then they always come up with one. Not one, identity matrix. Either way you do it, okay? So B is called the multiplicative inverse. We usually just say inverse of A. And a matrix that does not have an inverse is called non-invertible or singular. Okay? Why there's two terms, I'm not sure. There must be historically some reason for it. I don't know what that reason is. Might be a good paper topic if you want to look that up. Okay. Now, if a matrix is not square, it has no hope of having an inverse, okay? None whatsoever, okay? But just being square isn't enough to make it have an inverse. Again, so non-square matrices do not have inverses, period. So it's m by n by m. If those are not equal to each other, they cannot and do not have inverses at all possible. Okay, number one, because AB and BA could either not exist or they would have different sizes even if they could exist. Okay, so they can't have. Now, here's the next theorem. I'll write this down since you don't have your book today. If A is an invertible matrix, INV stands for invertible, then its inverse is unique. Okay, in other words, if A is a matrix that is invertible, there's only one and only one B that is an inverse. You can't have a series of inverse matrices. I'm going to choose that one.
So we're going to be finding the inverses.
That one and one only inverse. Exactly. That's exactly what we're going to be doing. Okay, and the inverse of A, rather than calling it B, we often call it A inverse. Now, just like we would with functional inverses, that's not 1 over A. Okay, whatever that you might suppose that to mean, that isn't the same thing. It's the inverse matrix. Okay.
Just raise all the little things to the -1 power.
Yeah, nope, don't even try it. Okay.
That just sounds terrible with all those fractions anyway.
All right. Okay. So everything we said before, A inverse is equal to A inverse A, and those are both I sub n. Whatever size A and A inverse is, I is that size too. All right, now what we're going to do next is show that two matrices are inverses. Here's A. -1, 2, -1, 1. Here's B. 1, -2, 1, -1. All right. What's that? Yeah, and that just happens to be the case in this one. Don't have that as a general rule. That we'll get to a general rule that only works for 2x2s, and it would work here. We'll get there, okay? So what we have to show, how can you show those are inverses of each other? Multiply them. So why don't we multiply them? What size will that be? 2x2, and what will that be when you multiply those? Okay. Below that. Okay. Yep. Got it. And sure enough, that's I2, and therefore, since AB is equal to I2, therefore, you know that BA is equal to I2. You want to do that one too, or you want to? Okay. It works too. They are commutative, and they'll come out to be that. They do show both of them. Now, they have a little remark, which we just already mentioned. Recall that it is not always true that AB is equal to BA, even when both products are defined. If A and B are both square matrices and AB is equal to I sub n, however, then it can be shown that BA is I sub n. That proof is omitted, so in example 1, they showed, it said you need only check that AB is equal to I2. You don't have to do it both ways. They did do it both ways, and it is. Now, let's do a different one. We'll see if your rule works. Oops. Okay. All right. All right. All right. Here, here's A. 1, -1, yeah. 4, -3. All right. Yeah, no, I'm sick. Okay. Okay. Sick minds. Okay. Find the inverse of that matrix. Now, here's the hard way. Huh? Multiply by some other matrix. What you want to call it? Let's call it. They call it X. I want to call it B. B11, B12, B21, B22. Okay? And we want this to be 1, 0, 0, 1. That's the goal. If we can find that, then we got our matrix, right? So how are we going to do that? Matrix multiplication. Yes, yes, yes. B1, yeah. Right. Yeah. 2, 1, right. And that's equal to 1. Okay. I'll get you choose. Okay. Negative B11 minus 3B21. Okay. What's that? Because we need one more. Okay. No, I'm putting like.
Oh, okay.
Yeah. Okay. Okay. Next.
And then we have negative B12.
Okay, which one are you doing now? Okay, yeah. Okay, yeah, got it. Okay. Negative B12. Okay.
Plus or minus negative 3B22. Or it would be.
Oh, wait.
Yeah, I'm doing the bottom right. This is
Okay, I'm sorry. I see what your question is now. Yeah. I was thinking we were going a different direction, but okay. What was that I just erased? A minus 3.
3B21.
3B21. No, don't do that. I've got to stop a moment here because I'm not sure what we're doing. Okay.
We're doing the wrong blank.
Yeah. B11
Yeah.
plus 4B21 is equal to 1.
Yeah.
Then we did minus, yeah, okay. Got it. Okay.
Yeah.
Okay, is equal to 0.
And
Got it.
instead of
Okay.
coming back up to the top, you can erase that negative B12 because I went to the wrong blank.
Okay. That's
So, yeah, I'm
okay.
in a really messed up order now.
Okay, yeah, that's so let's now actually there we have, let's just stop while we're there. The way you've done this, we have two equations, two unknown, let's solve them. And how could you do that? And what do you get? B21, right? Is equal to 1. Okay, so this is a 1 here. Okay. Nope. This is a 1. All right. All right. There we go. Okay, I'll get my pen back. All right, let's do the other. Now we don't need the blanks there anymore. In fact, let's. Yeah. Well. Okay, wait, wait a second. Okay. Oh, okay, yeah, Okay, now you want to get the other one. We got that to be a 1. So, yeah, doing that. Which one you want to use, top or bottom? I don't care. Huh, top? Bottom, okay. You have minus B11 minus 3 is equal to 0. So add 3 and you get negative 1, you get B11 is equal to negative 3, isn't it?
Yeah.
Okay, so B11 is a negative 3. Okay? All right.
Go on and do the other row.
Okay. And what would the first be then?
B12
Yeah. B12
plus 4B22.
B22 equal to?
It was an answer.
Huh?
It was 0.
0. Okay.
And then negative B12 minus 3B22 equals 1.
Okay. Again, add these and what do you get?
B22 equals 1.
Okay. And then plugging in.
You get the same thing.
B12
Equals 3, right?
is equal
Oh,
to,
no, it's not 3. Hold on. It's 3, 4, B4. Negative 4. Right?
okay,
B22 is 1.
right?
And then B12 is negative 4.
Negative 4. Okay. Ah! What does it do that? Okay. B12 is negative 4, B2, yeah, that's certainly right. Okay, so this is negative 4.
Then we can check it.
Okay. Did your rule work?
That wasn't a rule.
Okay, it wasn't a rule. Okay, so, all right. So, so you want to check that and just see? Let's do it. Okay. I know. I'm going to erase a bunch of stuff because I can't see. Okay. So what we're going to do is then, all right.
I got 1 and 0 for the first 2 columns.
1 and 0 for the first column.
Yeah.
Okay.
And then negative 4 plus positive 4 is 0. And then 4 plus 3 is 1. Negative minus 3 is 1.
Yeah. Sure enough, that's the inverse. Negative 3, negative 4, 1, 1.
Is there an easier way to do that?
Yes. Okay. Yeah.
I'm sitting here wanting to, like, thinking about it algebraically, like,
Right.
bring this one over here and set it equal to the unknown, you know
No.
what I'm saying?
Okay.
In my head.
Yeah. I don't know, can't follow quite what's in your head, but notice here is one thing we were doing. I wish I had left them up there now. Let's go back and do this. You had a B11
plus 4D21
plus 4B21 equal 1, and
negative B11 minus 3B21 equals 0. You want the other two?
yeah,
B12 plus 4B22 equals 0. And then negative B12 minus 3B22 equals 1.
okay. Now, if you did a matrix, I mean, we just did it by elimination by addition. That was so easy. But if you did a matrix, this would be a 1, 4, 1, minus 1, minus 3, 0. Okay? And you do this. And this would have been a 1, 4, 0, minus 1, you know. So why not? See, the coefficients are the same, right? It's just you changing this.
You're just changing
Yeah.
what they're equal to.
What they're equal to. So why not do them both at once and do, this would have been the matrix 1, 4, 1, minus 1, minus 3, 0. And this would have been the matrix 1, 4, 0, minus 1, minus 3, 1. Well, since you do the same thing for both, why don't we just do this? 1, 4, 1, 0, minus 1, minus 3, 0, 1. Which is just do them at once, and then row reduce. That's what we're really doing. We did it simpler than that, but we could have row reduced it and got the same thing.
Add the first one to the second row.
Yeah, exactly. Right. Okay. So let's do that. Row 1 plus row 2 is the new row 2. And that would, you use the first row, 1, 4, 1, 0. Okay. And 0, 1, 1, 1. And then you would have, you want that 4 to be a 0. So it'd be minus 4 row 2 plus row 1 is the new row 1. Okay? And that would have given, you're using row 2, 0, 1, 1, 1. This would have given you a 1.
Okay. I was looking down here. I wasn't actually.
Okay, sorry.
1 and
0,
0. And
negative 3.
and
A what?
negative
4.
4.
Okay, guess what you got? There is your inverse. This is exactly what that is, right?
Okay.
So what did you do? You started with your matrix, augmented that with your identity, and row reduced it till this became your identity, and that wound up being the inverse. There you have it. And that just doesn't work for 2 by 2s.
Okay.
It works for any size matrix.
Okay. So you take the original,
Yeah.
you augment it with the identity of the same size,
Right.
and then you
Row reduce.
and then it leaves you with the identity on the other side.
If you get the identity on the other side, then what you have there is the inverse. Exactly.
That's a lot better. I don't like all the
I know. Throwing.
substitution and
Yes.
all that. It's so much easier just to look at the numbers.
Exactly. Now,
A lot less writing too.
if you like that, okay, but anyway, let me write down since you don't have your thing today. Okay, that's all. Okay. Let A be a square matrix order n. Okay, that's going to say what? That says just what it says. Square matrix order n. Here's what you do. Write an n by 2n matrix consisting of A, A sub n augmented with I sub n. This is my shorthand. Okay. Write a n by 2n matrix. Yeah, exactly. This is the rule. Just saying. Okay. It consists of the matrix A on the left, n by n identity matrix on the right. I put the line in between. They don't. I like it there. Okay. This process is called adjoining the identity matrix to the matrix in question, matrix A. If possible, row reduce A using elementary row operations on the entire matrix AI, and if you get, after the row reduction, if you get I sub n B, then this B is A inverse. Exactly. Okay? If that works. If it doesn't, you don't. And then at the end, you can go back and check and make sure those are, and
So
if you've done the steps right, they will be.
if you can't get the identity matrix on the left,
It does not have an inverse. It's a singular matrix. Exactly. Okay.
So that, and if you tried to work it out, you probably get a row of zeros.
Yeah, that's what you would get. Yeah, at the bottom of the row of zeros. That, yeah, doesn't work. Linear algebra applied. Recall Hooke's law, which states relatively small deformations of an elastic object, the amount of deflection is directly proportional to the force causing the deformation. In a simply supported elastic beam subjected to multiple forces, the deflection D is related to the force W. If you have many forces, many deflections, then basically you get D is equal to FW. This is a vector, that's a vector. Deflections, forces, weights you might call them. This is the flexibility. F is a flexibility matrix whose entries depend on the materials in the beam. The inverse of the flexibility matrix, F sub inverse, so this is flexibility matrix, and this is called the stiffness matrix. The inverse of flexibility is stiffness. Okay, so the stiffness matrix, you can go on from there. So if this is of interest, it may not be of yours, but anyone else listening, if you happen to be in, say, mechanical engineering or some type of engineering that this would be of interest to you, maybe you might have some.
Interested in becoming a chiropractor or something.
Well, possibly. That would be. Yeah, as it said here, that's depending on the it says whose entries the flexibility matrix whose entries depend on the material in the beam. So I guess you could translate that to how rigid are the bones, or how strong are the muscles, or so that beam that you're talking about there for the chiropractor could be a human. So actually, it may not have a bad correlation there. There would be maybe a lot more variables there than would be in a steel beam. I don't know. Yes, exactly.
I don't think he would like that.
Probably not. So let's find one a little more challenging, but not a lot, than what we had. And this will be, here's your matrix A. 1, negative 1, 0. 1, 0, negative 1. Negative 6, 2, 3. All right. Okay, let's augment it. What do you put here?
1, 0, 0.
Got it.
1, 0, 0, 0, 1. You can read that whatever way you want.
Okay. Okay. Yes, I should have thought about that. Okay. First thing we want. What do you want first?
We want 1 in the top left-hand corner.
Got it. Done. Okay. Next.
We want to get a 0 below it.
Okay. And how would you get that?
Negative row 1.
Right.
Row 2.
Got it. That's your new row 2. Okay. So we're going to keep row 1 for now. 1 minus 1, 0, 1, 0, 0. Okay. Be sure you do the entire row, including the augment. Okay. And then what do you have now? 0, 1, negative 1, negative 1, 1, 0. Got it.
For the bottom row, let's do a 6 row 1 plus row 2.
Is the new row 3. Got it.
Plus row 3,
What's that?
I said the wrong row.
Yeah.
0.
0.
Negative 4.
Got it.
3.
3, 6, 0, and 1. What you want to happen next?
1 in the middle there where we got.
Okay, you got it. Good.
So we want a 0 below it
And above it.
and above it.
Okay, we're doing reduced row echelon form. Up and down. So to get the top one, what will you do?
We would do row 2 plus row 1.
Right, that's the new row 1. And what would that give you? Yeah, 0, 1, minus 1, minus 1, 1, 0. Okay.
So you have
1,
0,
0,
negative 1,
negative 1,
0,
0,
1,
1,
and
0. Got it. Next.
0. Alright, for the bottom, we do a negative, or no, a 4 times row 2, positive 4 times row 2, plus row 3.
Yeah, that's the new row 3. Got it.
So 0,
0,
0,
0,
1,
1. Is it? Yeah, negative 1, right.
2,
2,
4,
4, 1. Got it. What do we want to happen next?
have that bottom negative one become a regular one.
Okay, here's what I'm going to do. Make that a plus, minus, minus, minus. That was easy enough, wasn't it? Oh, it did it again. Okay.
And then we want zeros above that.
Okay, and how would you do that?
Add row 3 to
Row 3 plus row 1, and row 3 plus row 2. Okay. Row 3 stays the same. 0, 0, 1, negative 2, negative 4, negative 1. I hope I got it right. And then the top one becomes?
0.
No, 1. Top one. Okay, you doing the middle or?
I already wrote that part down.
Huh?
I wrote the part that wasn't going to change down already. It'd be 1, 0, 0.
Oh, okay. 1, 0, 0, 0, 1, 0. Okay.
Oh, yeah.
Hey, you said you wrote it, so I'm going to take your word for it. Okay. All right. Okay.
But it's alright, I got it now.
Okay.
Alright, so negative 2,
-2,
negative 3,
-3,
negative 1.
-1. Okay. Let's see if they got it right. Strange but true. Everything's negative, and that's so unusual. -2, -3, -1, -3, -3, -1, -2, -4, -1. Okay? Don't start trying to say, oh, this must be a pattern. No. If that first one had been all positive, this all negative, then you thought, oh, I think I discovered something. No. Because if that would have been true, then you could have said that all negative should become all positive, and it wouldn't have, because it would have given you that. So no. It's bizarre that it happened, but it did happen.
You got one spread here,
Yeah.
3's on an L, and then negative 2, negative 2, and then
There's no rhyme or reason. Yeah. Now, 2 by 2s, there is a little rhyme or reason. And I'm surprised we haven't hit that yet. But we will. We'll get to it. Now, if you want to multiply those two together and see if they come out the identity matrix, we take their word for it. Okay.
we did it once, that's good.
Yeah. All right.
Trust the math.
We got plenty of time, right?
About 30 minutes.
30 minutes. Good. Okay. Example 4. Show, what do we know about this matrix A? Here is 1, 2, 0, 3, negative 1, 2. 3, negative 1, 2, and negative 2, 3, negative 2. Yeah. Okay. What I'm going to do is, well, it's not coming up. What is the wrong? Oh, there it comes. This is so bizarre. Okay. And then we augment that with what?
Identity 3 matrix.
Right. And we start to work. And we already got the first what we want. So what do we do next?
-3 times row 1 plus row 2, and then -2 times row 1 plus row 3. So we want zeros below.
Okay. Row 1 stays the same. 1, 2, 0, 1, 0, 0. Row 2 now becomes
0. -7.
looks wonderful, doesn't it?
2. -3. 1, 0.
Okay.
And the last row, 0, 7, -2, 2, 0, 1.
Okay. Now, at this point, we can pause and say, wait a minute. Whatever you do here,
You're going to get zeros.
you're going to get zeros at the bottom.
That's singular. That's a singular matrix.
That's a singular matrix that does not have an inverse. That one right there doesn't have an inverse. There's nothing you can look at that and say, oh, I see why that doesn't have an inverse. Because I can. Okay. So. All right.
And that's it. That's all we got to do.
Yeah, that's all you really have to do. They skipped a bunch of steps when they did theirs. We skipped one, I guess. Now, the Gauss-Jordan elimination to find the inverse of a matrix works well even as a computer technique for inverses of size 3 by 3 or greater. So what we just did. The 2 by 2s, however, there is a formula that works much faster. Okay? Actually, as fast. Okay? So let's go back. I wish we had one with numbers. They do it with letters. This has nothing to do with this. This is just this. Let's just say we have a matrix A, which is A, B, C, D. Okay? Now, you can write down the inverse, A inverse, this way. This is 2 by 2s only. Okay? Actually, there is an easier way, but I'm going to show it to you in a minute. Okay? Well, no, this is the same. Okay. This is equal to. What we do, and we're going to do in the next chapter, in fact, we're going to do the determinant of that matrix. Do you remember what it is?
You have to has something to do with the diagonal.
Yes. It's this diagonal minus that diagonal.
That diagonal minus that diagonal.
Yeah, the main diagonal going from upper left
So
to
you
lower
add
right.
A and D minus
No, multiply.
Oh, A times D plus or minus
B times C. That's it. Okay? So, do that first. What is the determinant of A? AD minus BC. Okay? Now, first thing you do, divide by that. AD minus BC. Now, anything pop into your head right now? And it better not be 0. So
That's why it can't be a singular.
that would make it a singular matrix. If the determinant is 0, it's a singular matrix, non-invertible.
Okay, so once you get this, how do you turn that into the inverse?
Okay, that's the first step. Here's the next step. Okay, and this is a bit bizarre but true. Okay? Yeah. On your diagonals, okay, reverse them. The main diagonal.
So
dA goes there, okay, and then negate your other diagonals, minus B minus C, okay?
Okay, and then you multiply it by the.
Yeah. Right. So,
I'd like to see how this really works out.
okay, let's go back a page.
And just test it on one of the ones.
Yeah. Remember that one that you came up with a rule for?
No, I didn't.
Remember this one. Negative 1, 2, negative 1, 1. Okay? That was your matrix A. Okay? Now, what is its determinant?
That would be -1 minus -2, which would be +1 over
Yeah.
1, which
That
is
would
1.
be, yeah,
1.
1. And 1 over 1 is 1. Okay? So that would just be 1. And then what we're going to do is swap your main diagonal, 1 minus 1, and negate your back diagonal, minus 2, 1. Okay? And that's exactly what we had without doing any calculations, except for the determinant. And then moving a few terms around.
But this only works for 2 by 2.
Only works for a 2 by 2.
That's no good.
Yeah.
Go bigger with this.
Okay. Then the next one we did was 2 by 2 that we did was 1, 4, negative 1, negative 3. Okay. What would be its determinant?
Okay, that would be -3 +4.
Right.
1.
1. And that's why they came out with pretty nicely, because the determinants were 1. As you see a determinant not 1, you're going to wind up with a bunch of fractions in them. That's going to be the norm, not these. These are just nice, okay? But, okay, so you got a 1 there, and then so this one you do what?
That'd be -3,
-3, -4,
1.
and is that what we got? Sure enough, it is. Okay, now, so if you had seen in those first two this rule, you'd have thought, I have it. I can do a 2 by 2. You can do a 2 by 2 if its determinant is 1. But if it's anything other than 1, hang it up, Jack. You got other things to do. Okay. -1 would just be negating that. Okay. But anything else, any fraction or multiple or anything else, you're going to have fractions. Multiples or fractions. Okay. So that only works for a 2 by 2.
It's a shame.
It sure is, isn't it? All right.
Of course, then I don't know.
So let's actually find a couple more. Those were the easy ones that we had already done. Let's find some that we haven't done. Okay. Stand that. Okay. A is 3, -1, -2, 2. 3, -1, -2, 2. I think I said, yeah, -2, 2. Okay, let's do it with this new technique.
So your determinant
Yep,
would be 6
right.
plus 2.
Say again?
6 plus 2
Minus 2.
minus. Oh wait.
Yeah.
Okay, yes. It's not minus.
Yeah, you subtract the other product. And 6 minus 2 is
4.
4. So that's 1/4 of whatever we get next. And what do we get next?
2, 3, go on.
On the diagonal. Okay, gotcha.
And then 1, 2.
On that diagonal. So this happened to turn out all positive, didn't it? Okay. The negatives we notice, the positives we usually don't. Okay. Strange but true. What does this come out being then?
1/2.
1/2.
1/2.
Okay, going that way, yes, okay.
1/4. And 3/4.
Yeah. Which we would have loved if that was been the first one they gave us, right? But this is more the norm than the other.
And that would multiply through by 4 on both sides.
Well, you do. You could leave the 1/4 on the outside and leave the whole numbers on the inside. Yeah. Which I prefer. I don't like to go the extra step, but they did in the book, so I did it.
Yeah.
Okay? Let's do the B part, and this B matrix is 3 minus 1, negative 6, 2. Can you tell me anything right off the top? The what is? Yes, the determinant will be 0. The reason is this was a multiple of that. And 2 by 2s, they're pretty easy to detect, okay? Because they just sort of play out. 3 by 3s, it can be any linear combination of them, but a 2 by 2s, they're going to be multiples.
6 minus 6 is
6
0.
minus 6 is 0, so non-invertible or singular. Okay. Okay. I know that one is because I put a period there and that shifted.
Tap it, it's
Yeah.
gonna click.
All right. Now, properties of inverses. Okay. I think I will now go to a new one. Okay. All right. Theorem 2 lists the important properties of inverse matrices. Okay. Here's the givens. A invertible. Which means it's what? Okay. Which means it's square. Got to be square. Okay. K is a positive integer. Okay, K a positive integer. C a non-zero scalar. Okay. Let's look at positive integer. K has to be an integer. C is a scalar, but it's not 0. K could be 0. C cannot be. Okay? C could be negative. C could be a fraction. C could be an irrational number, but not 0. K can only be positive integers. Then, that's the given. Here is the conclusion. A inverse, a to the kth, remember we did that, positive integer, okay. CA, C being any non-zero scalar, and AT, what was that one? Transpose. Yeah, you flipped the rows and columns. I knew what you were signaling there. These are all invertible. Okay? The inverse of A certainly is invertible because that's the inverse. It gets back to being A. That was a given. The raise A to any power, you still have a square matrix, same dimension. Also, it's going to be invertible. Any non-zero constant times A is going to be invertible, and in the transpose of A, that should be fairly expected anyway, is also invertible. Okay. And the following are true. Okay. In addition to those 4 things, here's something else. This, hopefully, we basically already done it almost. A inverse, and take the inverse of that, guess what you get back to? A. Okay? Number 2. If you did A to the K, and take the inverse of that, now, this is bizarre, but it's true. Okay?